So continuing our discussion from the last video, in this video we're going to be looking at, for s orbitals, how they change as we change the principal quantum number and how the size of them changes. So all s orbitals, so here we're looking at s orbitals with three different principal quantum numbers. So we have a 1s orbital, a 2s orbital, and a 3s orbital. So these all have the same basic shape. We're looking at a cutout of them. Imagine this is like an orange. We've sliced it into quarters, and we're just looking at a quarter of it. And along the bottom here, we also have the radial distribution function. So this is the same plot we were looking at in the last video. We were looking at what's the probability of the electron as a function of the distance from the nucleus. And for the 2s orbital, we have this plot, and for the 3s orbital, we have this plot. So one thing to note is, again, the shape is the same for all of these orbitals. So it's L that sets the shape, and these all have the same value of L. But the size is different. And this is really important for understanding how electrons fit into atoms, as we're going to continue discussing this. And so the basic trend is that as n increases, the electron is further from the nucleus. And this is, of course, on average. So there's always some probability we can see even in these larger orbitals. Here with the 1s orbitals, the electrons can be very close to the nucleus, but even for the other, the 2s and 3s orbitals, there's still some probability of the electron being close to the nucleus. But the most probable distance where the electron is going to be the most often is a little bit further. So here for the 1s orbital, it's something around, I believe this peak here is at 54 picometers. And we can see here with the 2s orbital, the peak is about 250 picometers. And for the 3s orbital, the peak is about 650 picometers. So we can see there's a pretty clear trend here as we increase the value of n, as the principal quantum number increases, these orbitals get quite a bit larger. Right, so it's like 5 times further away from the nucleus, going from 1 to 2, and then it goes out to 650 picometers on average. So that's one thing to notice, is that we get different size of the orbitals. So the larger the orbital is, the higher the energy it is as well for the electrons. The other thing you'll notice, it's a little bit hard to see. It's pretty easy to see in the plots at the bottom. It's a little bit harder to see in the figures at the top. But there are what we call nodes that are present in our 2s and 3s orbitals that are not there in the 1s orbital. In the 1s orbital, there's the probability goes up and then back down. With the 2s and 3s orbitals, let me erase some of this so I can, whoops. Maybe I won't do that because I think it looks like I'll erase the whole picture. We'll just use a different color. I want to highlight these spots here, and they are highlighted, of course, with these dashed lines as well. These are the nodes. These are areas where psi squared is equal to 0, meaning the probability actually goes to 0. And if we're thinking about a wave, like a standing wave, which is what electrons are, they are waves as well as being particles, right? They have that wave-particle duality. That's what all this quantum mechanics stuff is about. If we have a vibrating string, say something like this, the string will vibrate up and down. If we imagine this as a sine wave, it'll move up and down, but there'll be a point in the middle here that doesn't move at all. And this is what we call a node. Oh, let's see if I can write that under my face. Barely fits. All right. So this is what we call a node. And we have an analogous thing. Now, this is a two-dimensional wave that I'm representing here. And with electrons, we're thinking about something that's spherical shaped, for an s orbital at least. And so these spots here, where the probability goes to 0, these are equivalent to this node over here. Now, the blue doesn't show up very well in the black, but you can see what I'm talking about. So these are represented. There are areas here at specific distances where the probability of the electron goes to 0. And these are at a specific radius. So this is a property of anything higher than an s orbital. And the number of nodes for an s orbital is equal to n minus 1. So that's why we have 0 nodes for an s orbital of a 1s orbital, because n equals 1 for a 1s orbital. But for a 2s orbital, we have 1 node. For a 3s orbital, we have 2 nodes. And that will go up as we go to higher and higher values of n. Similar to how we can have standing waves with more and more nodes in them. So that's what's going on here. So again, the takeaways here: s orbitals are all the orbitals with L equals 0. We can have different values of n. There are a bunch of different possible values of n where you can still have L equals 0. These are all spherically shaped, so the electron probability is shaped like a ball around the nucleus, and as we increase n, the electron is further and further away from the nucleus, and the energy increases as well. So that's our summary of s orbitals. In the next video, we're going to look at, as we increase L, as we look at L equals 1 and L equals 2, what do those orbitals look like?